My name is Holden Mays, and this is my video lab report for Lab 3 for Physics 2212 at Georgia Tech. This video will cover the lab in 6 sections, starting with an introduction followed by the measurements obtained during the lab, observations made during the lab, calculations done by hand during the lab, an explanation of the computational model used to visualize the experimental data, and closing with a couple of discussion questions. The goal of this lab was to measure the magnetic field of a bar magnet and calculate its magnetic dipole moment. A bar magnet produces a magnetic field that, for any individual magnet, varies only with the observation location's position relative to the magnet. By orienting a bar magnet so that its axis is aligned east to west, producing a magnetic field orthogonal to Earth's magnetic field, a magnetometer can be used to measure the strength of the magnetic field due to the bar magnet at various distances from the bar magnet. By plotting the natural log of the strength of the magnetic field at various positions parallel to the bar magnet against the natural log of the distance between the bar magnet and the magnetometer, the bar magnet's magnetic dipole moment can be calculated experimentally. The two laws most pertinent to this lab are the Biot-Savart law and the distance dependence equation for a magnetic field. The Biot-Savart law equation can be used to find the vector representing the magnetic field due to a single source at any given position r relative to a source of magnetic dipole moment mu. Combined with the distance dependence equation for a magnetic field, which uses values found experimentally, the value of the magnetic dipole moment can be calculated. The data shown here contains all of the measurements obtained during the lab, including a graph plotting the natural log of the strength of the magnetic field at various positions parallel to the bar magnet against the natural log of the distance between the bar magnet and the magnetometer, which will be used during the calculations portion of the lab. When the magnetometer is far away from the bar magnet, the measured magnitude of the magnetic field in the x direction approaches 0 microteslas. Conversely, as the magnetometer is brought closer to the bar magnet, the measured magnitude of the magnetic field in the x direction increases. By setting the value of r to 1, you can set the value of the magnitude of the magnetic field in the first two equations equal to each other to solve for mu, the magnetic dipole moment of the bar magnet. Mu was found to be 2.14 ampere meters squared. In this computational model, the gray cylinder in the center represents the bar magnet. The two orange arrows represent the direction and relative magnitude of the magnetic field due to the bar magnet at positions parallel to its axis. The four cyan arrows represent the same for positions perpendicular to the bar magnet's axis, and the single pink arrow represents the same for a single position that is 45 degrees above the bar magnet's axis. Shown here is the coding behind the computational model. The top box shows the function that creates the magnetic field at observation locations defined in the bottom box, as well as a single observation location defined later. The box on the left creates arrows representing the magnetic field at each of the previously defined observation locations, and the box on the right defines the observation location of a single arrow 45 degrees above the bar magnet's parallel axis, and then creates a pink arrow at that location. The output values from the computational model are displayed here, obtained when the distance between the bar magnet and the parallel and perpendicular observation locations is 18.5 centimeters. If we never compensated for Earth's magnetic field during this lab, the measured strength of the magnetic field at various observation locations would be different, either larger or smaller depending on whether Earth's magnetic field supported or opposed the magnetic field of the bar magnet at any given position. If two of the magnets used in this lab were stuck together and then used, the resulting magnetic fields would be stronger than if a single magnet were used. The magnet would theoretically double in strength, though in reality the increased size of the bar magnet would cause the resulting magnetic field to be short of doubled in magnitude.